Hey, what's up, you guys? Welcome back to another episode of Physics, and in today's episode we're going to do another internal energy problem. And this problem is going to be a little harder than the last problem, so let's go hit it. It's also going to be a long problem, so let's go hit it right now. And if you guys remember, last time I said that some problems you need to draw a system, some problems you don't have to draw a system, it just totally depends. So here, you and your friend Mike are going to a skateboard park, and when you get to the skateboard park, your friend Mike sees a box, grabs the box, gets in the box, and goes in the ramp, and he starts at this angle and goes woo, finishes right here, and you have one of those little drones, and you're right here in the middle of the ramp, and you find it very interesting that Mike stops right there because somehow he was going so fast, but he just stops right there. So you were like, man, what's going on? So you know that there's a friction coefficient, but you don't know how much. So that's A. And you're trying to find the final velocity here, and the question is asking to find an equation for the velocity final right here. So let's go hit it. The first thing we need to do is draw a system for this, because this problem is a little difficult because of the angle, especially. It's that ramp, and the angle is kind of difficult to find out the system right here. So let's go draw it right now. I had something like this, where it's the same angle right here, like that. It's that same angle right there with the box right here, and your friend Mike up here, and look at that, Mike's side right there. But yeah, so you know that the weight's pulling down, so that's mg, and there's a perpendicular and parallel, so this is going to be mg sine theta and mg cosine theta. And you know the friction's acting on your box, so friction's pulling you back, like it's slowing you down. So friction's pulling this way up there, so that will be frictional force. And you know that your normal force is pulling you that way, so it will be your normal force right here. And if I solve for those, I will have the normal force equals mg sine theta, because mg sine they're the same, and frictional force is normal force, frictional force, and this will be mg sine theta frictional, the friction coefficient. And if we start when I told you from last video that that energy initial has to be equals to energy final, I know that there's work plus potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final plus energy lost. Now there's no work going on in your problem, so work is 0. There's no kinetic energy initial because you're here, and technically you're at stop, so there is no kinetic energy initial, so it will be 0. And potential energy final, we can say that he's not stopped, so it's 0 too, so that's 0 0 0. So we are left with potential energy initial equals kinetic energy final plus energy loss. Now the problem with this problem is that how do you find energy lost? Like energy lost, and the thing is, it's kind of difficult because you're at an angle, so it's kind of hard to find the energy, how much energy loss you're losing. So I put here, where is the energy going? Where, like, you know the energy is losing, but how? Why? Where is the energy going? So I know that work has to be equals force times distance, r, distance traveled. And I know that the problem in here in this problem is that as Mike goes down with little box, and every little angle, the friction is acting, and he's slowing down. So I say that by saying that, like, for every little distance he's going down, friction is acting on it, and he's slowing down more and more and more. So I'm saying that dx has to be equals r d theta, representing every little tick I have in here. So I know that work right here, work. So I wrote this as S work equals F net times R, and F net, that's my friction force, and the distance traveled will be mg sine theta friction coefficient, RD theta, and I have those equations. I solved them back there. And if you have time, you can take every data, every angle of all these little ticks right here, and put the numbers in and solve for every little tick. But that will take you like a million years, and you'll be like a million, like 20 if you do that. So this is why you can do a little calculus in here and be like, if work equals my energy loss, and this is equal to the integral of SW, and SW is equal to the integral of mg sine theta the friction coefficient RD data, and this goes from 0 degrees to 90 degrees, and mg, u, and r are all constants, so I can pull all of them out. So I have this and this sine theta, and the integral of sine is negative cosine. If I plug in here, if I plug in 90, this is 0, and if I plug in 0 is 1. So I get something, and the negative will cancel because negative and negative 1 is multiply is just 1, so it will cancel. So I have mg frictional force R. So I know that work loss will be equals to mg frictional force R. And by knowing this, I can plug into my last equation and have something that mgr equals 1/2 mv2f and plus mg frictional coefficient R, and all my ends will cancel, and I'm solving for v here. So v equals the square root of 2gr 1 minus the friction coefficient. And that's how you find the velocity for this problem. I hope it helped. If you guys have any questions, please tell me in the comment section. So thank you.